Good morning, afternoon, and evening, everyone. Welcome to Observing Anyons 2020. This event is being hosted by the Virtual Science Forum, and let me give you a brief introduction. We are an organization of volunteer scientists who are seeking to improve the openness and accessibility of scientific communication. So in addition to events like this one, we host a bi-weekly long-range colloquium series called the Long Range Colloquium. For which our next seminar is next Wednesday, October 14th, given by Brian Skinner. We also have just launched a new platform called the Speaker's Corner, in which we seek to sort of upend the notion of invitations to give seminars. Here you will be able to invite yourself to give a seminar at the best possible time, which is the time that you have something to say. Such as when you've added a preprint to the archive. So at our website, you can see information about that. Today's focus, however, is to digest and discuss two recent and exciting experiments this year from Purdue and the Sorbonne, claiming the observation of fractional statistics. These are, of course, the headline experimental talks in the middle of the event. These results naturally build off decades of important experimental and theoretical work. And this mini conference is meant to be focused on these experiments, in part as an optimistic showcase of an exciting culmination of a long effort, and also to especially allow for a close examination of the accomplishments and provide an outlook for the future of the field. Now, during these seminars, you can ask questions direct in the chat directly to any of the organizers. That's myself, Babak Sarajeh, and Mesan Barkeshli, okay? And we will be able to alert the speaker to a question, to give the question at an appropriate time. And after the seminar, as time allows, given the timescale of the event, we'll allow people to raise their hands and ask questions that way in between talks. If you have questions in mind for the panel discussion, which is the concluding portion of the event, please also send them to us via the chat and indicate that it's for the panel, or you can send it to our email, to the conference email, anyons2020@virtualscienceforum.org, and we'll put that in the chat as well. And again, now that a few more people have joined, I remind you all that this event is recorded and will be published online afterwards, so keep that in mind, please. To begin, we have Steve Simon, a longtime theoretical leader in this area of physics, and we are very excited that he will be opening our event to describe the historical buildup to this year's experiments, and also to give us some pedagogical background to the underlying physics. Steve, take it away.
Okay, well, thank you very much, and may thank the organizers for putting together this nice conference, and particularly for inviting me to give the opening talk. The purpose of the talk, as we just heard, is to give you a little bit of theoretical background about anions, and also to talk a little bit about the history of how the field developed over the last 4 decades or so, leading up to the beautiful experiments that we're going to discuss today. I should mention right up front that this is really a very selective history that I'm going to be presenting. There's many other works in the field, many of which are extremely important, which I'm not going to highlight for lack of time. I'm trying to draw a continuous thread between the beginning of the field and where we are here. There are probably other ways that one could do it that would highlight some other works as well. So I apologize to people, authors of the works I'm not going to be able to talk about. So the story starts quite a long time ago with the simple question of what happens when you exchange 2 identical particles. 1924, with this famous letter from Bose to Einstein: "Respected sir, I venture to send you the accompanying article for your perusal and opinion." This is a rather bold move by Bose, but Einstein realized that what he was talking about was very important, and between the two of them, they invented what is now known as Bose-Einstein statistics, or bosons. The very next year, the Pauli exclusion principle was developed by Pauli, and immediately this resulted in Fermi-Dirac statistics, discovered not by Fermi or Dirac actually, but by Jordan, named after Fermi-Dirac because they published first a year later due to a bit of a historical accident. Anyway, by 1930, pretty much the basics of what we think of as modern quantum mechanics was finished. And if you want to include quantum field theory, that was more or less finished by 1950 or so. And you might ask, well, didn't anyone ask if there were things besides boson and fermions in the world? And in fact, people did ask this question, and there were attempts to define other things that were not bosons and fermions, things called parastatistics. But eventually these were found out to all be essentially bosons or fermions in disguise. And credit for that goes to a couple of researchers, Doppler, Hagen, Roberts in particular, in the early 1970s. It was only in this landmark paper in 1977 by the two Jans from Norway, Jan Magnalinus and Jan Merheim, where people started asking about lower dimensions. The situation is actually different in lower dimensions, that you can get different things which are not fermions and not bosons. In particular, what we now call anyons, we're going to be discussing the type of particle that when you exchange them clockwise, you get a phase e to the I theta, and when you exchange them counterclockwise, you get the opposite phase, e to the minus I theta. Now, you might ask, well, why is it that we didn't believe that such a thing could exist before that? Well, if you open up any quantum mechanics textbook, especially those written before 1977, they all have the following argument in them, that you can define an operator that exchanges two particles. And if you apply that operator twice, you get back to the original configuration. And the square root of 1, the identity operation, is plus or minus 1. So there's only two kinds of things you can have, something where you exchange them and you get plus 1, or you exchange them and you get minus 1 corresponding to bosons and fermions. And that really should be all. But in fact, that argument is incorrect in lower dimensions, because in 2 plus 1 dimensions, 2 exchanges is not equal to the identity. And it's useful to think here in some sort of space-time diagram, which fits very nicely with path integral ways of thinking. If you exchange two particles counterclockwise, as shown here, then you do the same thing again counterclockwise. The resulting picture is a knotted set of world lines, and this is not the same as two unknotted world lines. You can tell that by connecting up the top to the bottom and comparing it to something where the particles hadn't moved at all. And you see that on the left, you have a picture of knotted lines, and on the right, you have a picture of unknotted lines. And this is what tells us that 2 exchanges does not have to be equal to the identity in 2 plus 1 dimensions, whereas in 3 plus 1 dimensions, 2 exchanges does have to be the identity. This comes from the topological statement that you can't have knots in one-dimensional world lines in 3 plus 1 dimensions. Now, this topological statements about lines in 4 dimensions is something that's absolutely obvious to some people and completely obtuse to other people. I'll try to make it clear in just a couple lines. Now, I can't draw 4 dimensions, not even with the advantage of fancy PowerPoint. So I'm going to argue by a lower dimensional analogy. So let's imagine putting 2 particles on a line and ask, so this is 1 plus 1 dimensions, and we'll ask whether we can get them through each other, pass them through each other without them crashing into each other. And in fact, it's pretty obvious that you can't do that. No matter how you move them towards each other, they will crash into each other before getting to the other side. However, if instead I say, okay, now we're going to raise the number of dimensions that we're working in, instead of working in 1 plus 1 dimensions, now we work in 2 plus 1 dimensions, you can just move one particle out of the line and around the other, and then on its way, and they never had to touch each other. It's the same argument, we move up 1 dimension. In 2 plus 1 dimensions, you can imagine particle world lines which form an overcrossing like I've drawn here. Now, you might ask, well, is there some way to deform these 2 lines such that an overcrossing becomes an undercrossing? And obviously, as you move these two world lines around, there's no way to cross them through each other without them crashing into each other. However, if you allow us to move not in 2 plus 1 dimensions, but now in 3 plus 1 dimensions, you can just move this particle off this line, off into the additional dimension and reconstitute it on the other side. And then you've undone this knot without ever touching the 2 lines to each other. So in other words, you can't have knots in 3 plus 1 dimensions. And that means that you can only keep track of whether particles have exchanged or they haven't exchanged. And the original argument that you see in all the quantum mechanics books is then correct, that you only have bosons and fermions, but it's not true in lower dimensions. Okay, so the early history of anyons started with this paper by Linnaeus and Merheim in 1977. And in the first couple of years of its existence, not a lot of people paid any attention to it. In fact, the 5th citation of this paper was in 1982 by Frank Wilczek, which shows that not a lot of people maybe read it in its first couple of years. Wilczek popularized the idea and coined the word anyons. The very same year, 1982, of course, was the discovery of the fractional quantum Hall effect. The next year was the Laughlin theory of quantum Hall physics. The following year, Bert Halpern pointed out that you can consider the quasi-particles of fractional quantum Hall states to be anyons. And that discovery was put on firmer theoretical grounds by Arava, Schrieffer, and Wilczek, who did a careful Berry's phase calculation that shows when you adiabatically take one quasi-particle around another, you do pick up a fractional phase. Now that was way back in 1984, and here we are in 2020 with the first experiments that show this fairly convincingly now, or at least that's my opinion. How did we get from way back then to where we are here? These are the two experiments we're going to be talking about today. But before talking about these experiments, I want to say just a couple words about the big brother of the anyons that we'll be talking about today, the non-abelian anyons, which were more or less discovered around 1990 by a number of different groups, including people like Witten, string theorist, Froelich, and Moore and Seiberg. And then the following year, 1990, a paper by Moore and Reed that showed how non-abelian anyons can show up in the fractional quantum Hall effect. Now, the whole idea of non-abelian anyons was given a huge boost in 1997 by Kitaev's landmark paper explaining that certain types of non-abelian anyons can do quantum computation. That got a lot of people excited about the topic. Microsoft Station Q was formed to pursue this further. And I think, giving all due credit to the right people, our excitement about anyons these days, to a large extent, was spurred by this excitement about doing quantum computation. And a lot of the experiments that were done in the name of pursuing this idea of quantum computation. The anyons we're going to be talking about today, of course, will not be able to do anything like quantum computation. That will all be discussed another day, and maybe there will be further experiments talking about non-abelian anyons, but that's not what we're going to discuss today. So these are the two experiments, and I'm going to start by discussing the historical development that led up to this paper by the Purdue group, which you'll hear from Jimmy Nakamura and Mike Manfra later on today. So I think the historical development of this idea actually goes back to a paper by Steve Kivelson in 1990, where he points out that by doing interference experiments around a dot or an antidot, you should be able to, in principle, measure the statistics of quasi-particles. That was fleshed out into a much more definite type of experimental proposal by Claudio Shimon, Denise Fried, Steve Kivelson, Shivaji Santi, and Xiaogan Wen. This is more the picture from their paper, which is, qualitatively quite similar to what has actually been done in these experiments. Now, the idea of doing the experiments was 1997, and the well, actually, let me first explain what the experiment's about. So this is a picture of a quantum Hall bar. The blue part is supposed to be electrons, quantum Hall fluid, and then the Hall bar has been pinched down at 2 points, which we can think of as a beam splitter and a mirror, places where the particles can jump across this narrow neck. So we can think of the edge states of the quantum Hall effect as quasi-particles running along these edges, but sometimes when they get to this beam splitter, they can split into two partial waves like this, like a half silvered mirror. One of the partial waves can go around the cavity, come back and re-interfere with the other partial wave, and then go on its way after having some interference. So this is obviously an electronic analog of what we think of as Fabry-Perot interferometry with light. Now, what we have at our disposal in the experiment that we can change is the flux through the cavity here, and the gate voltage, some sort of side gate voltage, which changes the perimeter of the path. And as you change, for example, the side gate voltage, we will see interference fringes as the interference of the two partial waves becomes constructive, followed by destructive, followed by constructive again. So this is a signal that one wants to see. The signal that is supposed to show us that we have some sort of anion statistics is that if you add an additional quasi-particle in the center of this cavity, the interference pattern should shift by 2 pi over 3 or 4 pi over 3, depending which way you look at it, corresponding to the statistics of the anyons, because we have one anion here wrapping around another anion, having been exchanged twice to go all the way around. Let's see that again, nice animation, and re-interfering with this other partial wave. So each time you add a quasi-particle into the center of the loop, we pick up a factor of this theta anion, and the interference pattern will shift over by some fraction of 2 pi, which is what one wants to measure. Now, this the proposal for this experiment was in 1997. It was attempted in the early 2000s, primarily by Vladimir Goldman. He did indeed see some oscillations, which seem to correspond to destructive and constructive interference, both with gate voltage and magnetic field. But there was an awful lot of confusion about this data because it didn't seem to make a lot of sense. It didn't seem to fit with what was initially predicted, despite the title of the paper. A lot of this was sorted out by 2 very nice papers by Rosenau and Halpern, and then Rosenau, Stern, Nader, and Halpern in 2007 and 2011. And the moral of these two papers is that the charging effects inside the dot can be extremely crucial to what you actually see. So the second paper does quite a nice job of explaining what it is that one might see in these experiments. And what's plotted here are what we now call pajama patterns for, presumably people's pajamas look like this. We have 2 axes on each of these plots, magnetic field along the bottom axis and the side gate voltage along the vertical axis. Now, depending on the particular sample that one is using, this sample can have lots of charging effects, and in which case you're way over here on the right, strong charging effects, and call that Coulomb dominated, or you can have no charging effects, which we call a Aharonov-Bohm. And the pajama patterns for these 2 different possibilities have slopes going in the opposite direction. For Aharonov-Bohm, the slope is going down and to the right, whereas for Coulomb dominated, you have it going up and to the right. Now, the original theoretical discussions of this type of experiment were all discussing the Aharonov-Bohm regime, where there are no charging effects in the dot, but most of the experiments that were done were actually in this Coulomb dominated regime. Or another way to say this is that we had this formula for the interference phase that you pick up, which has a factor of the flux and the side gate voltage over here, and then the number of anyons you go around. But there's another term, which is a Coulomb correction. And if you're in the Coulomb dominated regime, way over here, where you have strong charging effects, the Coulomb correction dominates everything, and you don't have an ability to measure the statistical phase of the anion at all in the Coulomb dominated regime. You have to be over in the Aharonov-Bohm regime to be able to measure the statistical phase of wrapping one anion around another. Now, a number of experimental groups went after this and found indeed that if you go to a large dot, a large interferometer, then the charging effects are small and you get to the Aharonov-Bohm regime. And if you go to a small interferometer, then the charging effects are large and you're in the Coulomb dominated regime. So this looks beautiful. So you might say, okay, go to the small charging regime and do your experiment here. Lots of other groups did the same thing, found more or less the same results, that if you have a small dot, you get Coulomb dominated, large dot, you have Aharonov-Bohm. So maybe you would say, well, go to the Aharonov-Bohm regime, but it's not so simple. No one ever saw Aharonov-Bohm pajama patterns in the fractional quantum Hall regime. It seemed that you had an option. Either you could see fractional quantum Hall physics, but you were Coulomb dominated, or you could see Aharonov-Bohm physics, but you were only getting interference for integer quantum Hall effect. So this was a little frustrating. It was even more frustrating because Moti Heiblum's group at the Weizmann had a different type of interferometer, Mach-Zehnder interferometer, with lots of beautiful experiments associated with that setup, which never saw any interference in the fractional quantum Hall effect, for the fractional quantum Hall effect either. So we were having, it seems that nature was being rather unkind to us and never getting interference of fractional quantum Hall edges in the regime that we needed. There were some rays of hope, or possibly rays of confusion. There's this a number of papers from Willett over the course of several years, which suggested that he was seeing small dot, even though he was in a very small dot, he was seeing interference that appeared to be a Aharonov-Bohm regime, which is what you would need to see the statistical angle of the anyons. The problem here is that these were not pajama patterns. It was not very periodic. I mean, these are sort of slightly periodic, vaguely periodic signals. And that's the reason why we couldn't get pajama patterns. And of course, they were not measuring statistics yet. Nonetheless, it was suggestive that one might be able to get some data, even from small dots, that was in the Aharonov-Bohm regime if you did the right things. There's also this experiment from Wan Kang's group. Full disclosure, I was one of the co-authors. In his first attempt to take data from nucleus 7/3, he saw beautiful phase slips between different curves that were separated by 2 pi over 3. So this is exactly, if you back up to this picture here, it's exactly, phase slip between these two different patterns, which seem to differ by 1 quasi-particle in the middle. The problem with this data is that we knew pretty well that this was a Coulomb-dominated sample, and so we really didn't expect to have phase slips which were exactly 2 pi over 3. We had a paper, myself and Bernd Rosenau, which gave a scenario by which phase slips could still be close to quantized. However, it wasn't incredibly convincing without more data, and the real problem here was that the data did not reproduce. Even though this was the first data that was taken, even after much trying, did not seem to be that reproducible. So that was frustrating as well. The big breakthrough came last year, 2019, with this beautiful paper from the Purdue group. What they realized was that the problem seems to be that it's hard to get into the Aharonov-Bohm regime. It's hard to get the charging energies small enough so that you're not dominated entirely by the charging energy of the dot. And the way they managed to get rid of this charging energy was by growing a special structure where the two-dimensional electron gas you're interested in, where the fractional quantum Hall effect is living, is in the middle. And then on both sides, you have additional electron gases whose only purpose is to reduce the charging energy of everything going on within this one quantum well. And this beautifully puts you in the Aharonov-Bohm regime and takes you up to the experiment that you'll hear about today. Right, and so more or less what they see is they see phase slips between different oscillations which are separated by exactly this, or very close to this phase 2 pi over 3. Okay, so that's the brief discussion of the history of this lower paper here. Then this upper paper here, the fractional statistics in anion collisions, sort of takes a slightly different history. The history of this paper probably starts with this paper by Kane and Fisher in 1994, a theoretical paper, where they proposed that you could measure the fractional charge of the quasi-particles in the fractional quantum Hall effect by doing shot noise measurements. Now, this suggestion was rather quickly taken up by both the French group and the Weissman group, and what they found was that by making a small constriction in the quantum Hall bar, that the shot noise through that constriction fit a description of being in units of E over 3 rather than in units of E, proving for the first time that the charge of the quasi-particle in the fractional quantum Hall effect is E over 3 rather than E. Now, this was a rather important set of experiments for several reasons. First of all, it was the first direct observation of the fractional charged quasi-particles. Secondly, it was cited extremely prominently in the Nobel Prize that was awarded the following year to Suey, Stormer, and Laughlin. But something I think that is at least as important as these things is that this became a technology, that the techniques that were used to measure this type of shot noise were then used for lots and lots of other great experiments, measuring noise correlations, measuring thermal transport. All of these things are wonderful, wonderful experiments that really started, I think, with these two experiments here. I'm going to sort of trace through the history of some of the experiments that were done with the same type of techniques leading up to what we have now. So to some extent, the experiments that were done thereafter recapitulated the history of quantum optics. So in quantum optics, we have this effect known as Hanbury, Brown, and Twist. Hanbury, Brown is one person, Twist is another person, where you send coherent light into a half-silvered mirror, and you discover that the bosons, or the photons coming out of the half-silvered mirror, have a tendency to bunch. They either come out in bunches at one detector or bunches at the other detector, and then they switch back and forth between the two detectors. Now, this was done in photons way back when, but people decided, oh, well, you can actually do the same experiment with electrons by using quantum Hall edges. And this experiment was actually proposed much earlier by Marcus Büdeker. Was done by Klaus Enslin's group using a single point contact as the beam splitter and quantum Hall edges as the electrons follow the quantum Hall edges as their path. Beautifully showed that whereas bosons bunch, the fermions have the opposite tendency, they anti-bunch. A different version of this experiment, a more sophisticated version of this experiment, was done by Hanbury, Brown, and Twiss in 1956, where they showed that you can interfere photons from different sources. The same experiment was done in electrons, again proposed by Marcus Büdeker's group, done in this case by the Weissman group, again using integer quantum Hall edges and quantum point contacts as the half-silvered mirrors. Again showing the same type of physics as bosons, except the opposite, that bosons bunch, but fermions anti-bunch. They have a tendency two fermions hitting the mirror at the same time have a tendency to come out at opposite detectors. Another version of this experiment in quantum optics is known as the Hong-Ou-Mandel experiment. It was done somewhat later because it's done with single photons, and single photon technology wasn't developed until somewhat later. The idea is you send single photons into a half-silvered mirror, and the single photons have a tendency to bunch. If the two photons arrive at the mirror at the same time, they have a tendency to bunch and go towards the same detector. This same experiment was then done by Gwendol Fev's group. Gwendol will be talking, I believe, right after me. And what he found, so he did exactly the same experiment, the half-silver mirror here, except with fermions. And quantum Hall edge states. So the electrons run along the quantum Hall edge states. They reach a half-silver mirror. That's a quantum point contact. And the trick here is to use single electrons. And the way you source the single electrons is by spitting them out of a quantum dot. And indeed, what he found was that when the electrons reach the beam splitter at the same time, they have a tendency to go out to opposite detectors. Okay, so all of these experiments that I've been talking about have been experiments with bosons and fermions, but what about anyons? Well, there's a long history of, starting in about 2001, of theorists talking about trying to observe the same type of correlations, but with anyons. So the first paper of this sort was by Ines Safi, Pierre Devillard, and Thierry Martin. And their conclusion, which is a rather important conclusion, is that fractional statistics do have an important effect on any sort of current correlations or noise measurements that you do on multiple terminal experiments. The first experiment that they proposed was probably an experiment that was not actually plausible to make experimentally, but then over the course of many years, different versions of this experiment were proposed, and it was, people thought more seriously about what could actually be measured and how clearly you could measure the fractional statistics. Smitha Vishweshwara was one of the people who was very involved in this, and she's on our panel later, and she'll say a couple words about this development as well. So I think the evolution of this field theoretically was really aiming towards finding experiments that were more compelling and more convincing that you've actually measured fractional statistics. I want to highlight this experiment, this theoretical work in particular. They describe an extremely complicated experiment that you might say, okay, this looks like it's crazy complicated to try to build, but it's actually not that much more complicated than some of the experiments that Modi Heiboom had been building at the time, although his experiments were all done with integer quantum Hall edges, and upgrading to fractional quantum Hall edges might have been a problem. But nonetheless, it's not that much more complicated. The thing that's particularly interesting about this experiment was that the Hanbury, Brown, and Twiss, I think the hyphenation is in the wrong place here. Hanbury Brown is one name, Twiss is another name. I don't know why it's hyphenated this way. I'll have to try to figure that out. So what was interesting about this particular experiment is it's arranged such that the anyons can go around each other, but they never get near each other, which is fairly important because the anyons can be charged, and you don't want to confound your results by worrying about the charges on particles. The experiment that was actually done, the one that we'll hear about, is this experiment proposed by Bernd Rosenau, Ivan Levkovitsky, and Bert Halpern. It looks kind of complicated, but actually it's really pretty simple. It has 3-point contacts, but the interesting quantum point contact is the one here in the middle. The 2 quantum point contacts at the sides, their only purpose is to create a dilute gas of quasiparticles or charge bumps running along the edge. So this quantum point contact 2 here, okay, this source 4 is put at voltage. So there'll be some jump of quasiparticles across, oops, back up, jump of quasiparticles across this narrow neck, and you'll have a dilute gas of quasiparticles running around this edge and coming to this quantum point contact. Similarly over here, S1 is put at voltage, and you'll have some number of quasiparticles jumping across this contact, and then coming along this edge, there'll be a dilute gas of quasiparticles coming to the quantum point contact. So it's very similar to the Hong-Ou-Mandel setup, where you're sending quasiparticles towards a single beam splitter from opposite directions and asking whether they come out at the same or at opposite drains. So when you straighten out all of the wiring here, you have a dilute gas of anions coming into a single beam splitter here, and then you're measuring the correlation between the outputs at drain 1 and drain 2. So a calculation was done, and what was found is that there's a negative correlation between the outputs at drain 2 and drain 3. That negative correlation corresponds to a bunching behavior, which you might say makes it seem more like bosons than it is like fermions. And it's certainly not fermionic behavior, not even interacting fermionic behavior would give this. So that's nice as a start. In fact, what is measured is essentially the exact correct prediction for a model that has non-interacting anions of charge E over 3 and statistical angle 2 pi over 3 as well. So it appears that the interaction between the anions is not important. It seems to agree perfectly with the experiment. So I've used up about my half hour at this point. These are the 2 experiments you're going to hear about in a moment. I'm happy to, if there's a few minutes left, I'm happy to take questions. If there's not a few minutes left, I'll stand down. But if there are questions, I would sort of encourage you not to ask questions about things that the experimentalists should be answering, or that we should be waiting to hear from the experimentalists first before trying to answer. And thank you for your attention.
Thank you, Steve. There was one question that came up in the chat during the seminar, which I'll start with, and then others can please raise their hand, and I'll call on you then. The question from the chat was, could you please comment on? Oh, hold on, I don't have it all. Here we go. Could you please comment on the permutation symmetry basis of the boson fermion classification vis-a-vis the holonomy or braiding picture, which also allows for anionic statistics? This was around slide. This is very early in your talk. It was right. Yeah. Okay.
So
by Rudro Biswas for those. Yeah. Okay.
Okay. So I'm not exactly sure what the question is asking me to clarify, but let me say a couple words which might be a little bit more clarifying. So in the difference between 2 dimensions and 3 dimensions, one way of thinking about it is that in 2 dimensions, the paths particles can take are classified by braids that can knot with each other, and there's a group of braids you can perform. There's operations in the sense that you can perform one braid, then perform another to make a longer braid, so you can multiply braids together and so forth. Whereas in 3 dimensions, since knots can always be untied, you can have you only have permutations, so that any set of paths can be described by its permutation. Permutation of the particles from the beginning to the end. And so what this essentially means is that in 2 dimensions, 2+1 dimensions, your particle statistics should be a representation of the braid group, whereas in 3+1 dimensions, your particle statistics should be a representation of the permutation group. And if you're thinking about abelian particles, then there's only two one-dimensional representations of the permutation group, which is the symmetric and alternating representations, which correspond to bosons and fermions. If you're interested in non-abelian representations, there are higher dimensional non-abelian representations of the permutation group, and it's actually there's a rather subtle theorem, which was what was worked out by Doppler, Haag, and Roberts in the early 1970s, which proves that none of them make a valid description of, under some very general assumptions, that none of the higher dimensional permutation representations make a valid description of particle types. I hope that's answered the question, although I may have been completely off base when I was answering.
Yeah,
Send me email if I didn't answer. So.
Sure. Yeah. So Rudro has thanked for the answer. So okay. I suppose it's good. We have another question in the panelist by Yuval Ronen. Yuval, you should be able to unmute yourself now for a moment.
Thanks. Thanks for a beautiful talk, Steve. I wanted to ask, what is the, if this is like indeed braiding of anion particles, what is the next goal for abelian anion?
Yeah. Oh, for abelian anions. Well,
yeah, non-abelian, it's clear. Yeah.
Yeah. So I think at this point there's still quite a few goals for abelian anions. So both of these experiments, as you'll see, have focused on just Laughlin states, nu equals 1/3. And it's not so clear that everything is simple when you go to nu equals, say, 2/5 or some a hierarchy state. So even with abelian quantum Hall states, there's still work to be done. Although maybe I'll be surprised and I'll discover there's new data that I haven't seen yet of the other quantum Hall states. But at least the published data that I remember is all at nu equals 1/3, which is a simple Laughlin state. And then you can start thinking about the hierarchy states and Jane states and seeing whether they fit the model as well. So I would say that's the next goal.
Okay, I think we have time for maybe two more questions.
Can I make a remark, Moti Heiblum?
Sure.
Yeah.
Okay, I just want to say, Steve, indeed, when you have two particles that hit each other, you can see if they are boson, fermions, independent, etc. But when we do cross correlation, we see many events. Most of the events are when one particle comes, the other side is 0, and the other way around, right? Because it's highly diluted. So if you don't do anything, you always get negative cross correlation. Okay, if they don't, let's say they don't hit each other at all, you get negative cross correlation because it's 1, 0, 0, 1, right? Even if it's independent particles, two that don't know each other, you'll get negative.
It's been normalized, and so let's put it this way: Wait,
I didn't finish the.
Oh, go ahead. Sorry. Yeah, go ahead.
I'm just saying that if you just look on the non-interacting part, non-touching part, you get negative. So it's very easy to get negative. The point is that even if they don't know each other, you'll get negative. So the point here in the result that you get -2 has to do only with theory, which I don't understand even. Okay.
So
for electrons to get 0, it's kind of a miracle that there is cancellation.
Okay, I see. I understand what you're saying. Okay.
Yeah.
Well, okay, yeah.
We can certainly dig into this more, especially in the panel discussion. I think this would be a good topic for that.
Let's bring that back up in the panel discussion. I agree. Yeah. Okay.
Eduardo had a question. Let me ask him to unmute. Eduardo, I think you should be able to pose your question now.
Yeah, it's just a comment. I think there is no meaning to the concept of non-interacting anion. The braid statistics requires that they are strongly coupled at least at short distances, so the braiding is actually stable. And people have tried to actually construct distribution functions intermediate between bosons and fermions, and those are all inconsistent. So I think in my opinion, it's an inconvenient language. There is no free anion model that you can write.
Sure. So let me rephrase that. When I said non-interacting anions, what I meant was that the model is not giving them Coulomb interactions, long-range Coulomb interactions, which you could put or not put. So you could, for example, consider a Laughlin state with a ultra short range Hamiltonian, the quasi-particles of which would not have long range Coulomb interactions. And you could consider that model. That's what I mean by non-interacting anyons. But I agree that because of the statistical interactions, that's saying that it's non-interacting is maybe not exactly the right words.
Great. I think we are at a point where it would be good to transition